Okay, so last time we have introduced you the k-means and also the kernel k-means, right? And now we're going to introduce you another famous clustering algorithm. Okay, but before we introduce this algorithm, okay, let's first check against the basic idea behind the clustering, right? So actually, in the clustering, there are two main criteria we usually expect for, okay, in the result. The first one is the compactness, okay? So the compactness is just like this. So we would like to group the data points. We would like to group the data points such that you can observe some, compact clusters in the result. Okay, so for example, all the data points in a single cluster, they are quite close to each other. Okay, so this is the compactness. Okay, so in the k-means or the mixture models, you do see such compactness. Okay, and another important criterion that usually you can see from some clustering algorithms is about the connectivity, right? So for instance, in the figure here, you can see that given such data set for our human being, we would naturally form a cluster for the outer circle and another cluster for the inner circle, right? So basically, in this figure, right, we would like to cluster the data points with strong connections together. So for instance, the data points on the outer circle, they do have strong connections, right? For example, here this data point is with strong connections to its neighbor, and uh, have its neighbors have strong connection to another data point and so on. So you can use this kind of strong connection to keep growing your cluster, and in the end, all the points belonging to the outer circle will be clustered into one group, and the points in the inner circle will become another one. Okay, so the connectivity is actually a very natural and very intuitive way for human beings to define the clustering, right? So actually, we would like to use this kind of idea in the design of the clustering algorithm. So the algorithm that we are going to introduce you later, okay, the special clustering is mainly depends on this kind of property to perform the clustering. Okay, so the special clustering, this algorithm was introduced back to 1970. So you can see this is quite early. Early it's already quite early. Okay, it's back to I don't know almost like 50 years ago, right? And it's actually still quite popular as it can find clusters of almost arbitrary shape. So this can be also told from this kind of figure, right? And that time we say actually the k-means algorithm, okay, it is suitable. It can only produce the clusters which might be, linearly separable, right? Okay, and if you want to deal with more complicated cases, right? So for instance, in these cases of having nonlinear non-linearly separable groups, then you should look for uh, alternative alternative of using the kernel, right? So that means you need to first project your data to some feature space, then perform k-means over there, right? Okay, but for the special clustering, actually it is confined cluster of almost arbitrary shape because it mainly considers the connectivity. Okay, so um, so that is quite important, and that is why a lot of people, a lot of people like to use such a clustering algorithm, and it has a very beautiful theoretical background behind it. Okay, so that is why a lot of people like it because it has a very strong support from the theorem. Okay, okay, and let's start with let's first start from the graph clustering. Okay, uh, that is the basic for the spatial clustering, right? The graph clustering is actually quite easy to understand. So, for instance, you are given a set V of data points S1 to Fn, that is your data set, and also you are given their similarity, right? You do have the similarity for every pair of the data points, right? Okay, so the similarity here we use W, okay, and then when you are given this data set and their similarity, then you try to partition the data into groups such that the points in the group are similar and the points in different groups they are dissimilar, right? Okay, this is quite straightforward, and this is actually your goal, right? And now we can build up a similarity graph, okay, by using this element, right? You can first treat your data point as a lot of vertices or the nodes, okay? And then you can build up the edge. You can build the edge between the data points, right? So for example, I can try to connect these two data points once their similarity value is bigger than 0, right? Okay, and the weight of this edge is defined based on their similarity. Okay, so now you turn from your data point and the pairwise similarity into this similarity graph. Okay, so you can denote this graph by using G of VEW, the node of your data point, the age if a data point pair if for a data point pair its similarity is bigger than 0, right, and the W, right, basically the age weight defined based on the similarity. Okay, so you can have a similarity graph like this. Okay, so now we try to once we have this similarity graph, we try to partition this graph such that the edges within a group have large weight. So that means the data points now being assigned to the same group, they have strong similarities to each other, right? And also the edges across the groups should have small weight. That means that for the data points, if they are belonging to different groups, then their similarity should be pretty small. That means they are dissimilar. Okay. So now, uh, so, so, so now basically in this similarity graph, okay, because you will first define the age, and most of the time, okay, it's of course it of course depends on what kind of similarity you use, right? But most of the time, the similarity and the ages built upon the similarity is trying to model the local neighborhood relation, right? Okay, so if I am if for that point xi has pretty strong similarity to another point xj, then if you try to draw out this similarity graph, then you can see that very possibly the xj is the neighbors of is one of the neighbors of xi, right? So basically, this kind of similarity graph is trying to model the local neighborhood relations between the data points, right? So Okay, so you can use your you can have your own way to define the similarity measures between the data points, right? For instance, like this is actually a quite popular choice, right? You can use you can use the Gaussian kernel similarity function, right? So for example, the L2 is potential to the L2 known divided by 2 sigma square. Okay, we can use this way to define the similarities between the data points. Okay, and actually in this kind of similarity function, you have these parameters sigma, and this is somehow to control the size of neighborhood, right? Okay. Okay, so when you use this kind of similarity function to describe the pairwise similarities, okay, between the data points, then you can build out a graph, maybe like this way, okay. You have a lot of nodes representing the data point, and the age indicates if these two data, if for any two of the data points, if they are the neighbors, okay, and the weight of each age is defined by the similarity, okay, okay. So again, you are given this kind of data set that you have x1 to xn and their similarity, okay, w. And now you want to partition the data. You want to partition the data into groups, okay? And you can first build up the similarity graph, okay? G of V, W. Here we just simply ignore E because E is fully depends on the W, okay? So this is just a simpler way to write it, okay? So basically, this similarity graph, it has a property, right? It is basically a symmetric matrix. It is a symmetric matrix, right? So this is easy to understand, right? Because the similarity matrix, right, is basically define the pairwise similarity, right? It includes the pairwise similarity, right? So you can see here each row and each column, okay, you can see that actually this matrix is symmetric. It is symmetric. Okay, this is quite easy to see. Okay, and all of the elements were bigger than 0. Okay, all the elements were bigger than 0 if the RBF kernel is used, right? So for example, if you are using this kind of similarity function, right? Then because you can see because this is related to a Gaussian kernel, right? So no matter how far between the xi and xj, there is always a positive value, right? When you compute their similarity, there will be always a positive value. So if you are using a RBF kernel to define the similarities between the data points, then all the elements in this similarity graph were bigger than 0, right? But of course, if you use another way to define the similarity, maybe some values will be equal to 0, right? And we also define for every node, that means for every data point, okay, we define a specific term named degree, okay? So the degree is actually the summation of the weight from these data points to all the others, okay? So for instance, you are given a data point V, right? And then we try to compute its similarity to all the other data points, and then we sum up all those weights. Okay, so basically this idea can be expressed by this term, right? So you have your similarity graph W, right? and then you want to compute the degree for a certain data point V, right? And you simply sum up, you simply perform the summation on the on the okay on the rows on the row related to that data point in your similarity matrix, right? So for instance, right, maybe this data point is V, and now I want to compute its degree, then actually the computation is based on performing the summation over this row, okay, over this row, because that means the pairwise distance from a pairwise similarity from these specific data points to all the others, right? Okay. And the degree matrix, right? So once we compute the degrees for all the data points, right? Then we can build up a new matrix, so-called degree matrix. Okay. So the degree matrix, its size is still n by n. So here, as you can see, right, you have so many data points. You have n data points. Then you can build up a n by n matrix. Okay, this matrix is the degree matrix, and all the elements in this degree matrix is defined by using this way. Okay, so the U on the VU location of this degree matrix, okay, such element is equal to dV, okay, the degree of the degree of the node V times a delta function VU, okay. So the definition of the delta function, is like this, okay. You have let me try to insert this question. Okay, so the delta VU equals to 1 if, okay, wait me a second. If V equal to U, okay. And 0 otherwise. Okay, so the definition of this delta VU, okay, is like this, right? It will be equal to 1 if V equal to U and 0 otherwise. So you can think that this degree matrix will be a diagonal matrix, right? It will be a diagonal matrix. Okay, it only has values on the diagonal, right? It only has values on the diagonal. Then for the elements on the diagonal, it records the degrees for every data point. Okay, so basically that is the degree matrix. Okay, so again, we show you a example of the similarity graph. Okay, and actually we say most of the time the similarity graph is trying to model the neighborhood relations, right? So if you do have some specific definition of the similarity, then maybe for a single data point is only connect to some neighbors, a small group of neighbors. So in this kind of similarity graph, we only count the neighbors. Right? And here comes an example. of the similarity matrix right? Okay, so this is just a real example of the similarity matrix. Okay, and if you try to see such similarity matrix, okay, so basically from this similarity matrix is has fully described all the things in a similarity graph, right? Okay, so given this similarity matrix, right? Now assume we would like to consider a simple case that we would like to decompose, or we would like to partition these similarity graph into only two sets. Okay, so that means we would like to perform the clustering on this data set and to have two clusters in the end. Okay. Okay. So let's now assume these two clusters are denoted by A and B. Okay. So now that means we will partition the graph into two sets A and B, such that the weight of edges connecting vertices in A to vertices in B is minimal, right? It's minimal, right? So that means we would like to make the data point, the similarity between the data points across A and B to be small. In other words, we would like to have the data points across A and B, they are dissimilar to each other. Okay, so that is why we would like to minimize the weight of the edges connecting across A and B. Okay, so we would like, for instance, in this similarity graph, we would like to minimize the summation of those edges connecting across the group A and the group B. Okay, so if you write down the equation here, okay, then it can be written down as the equation here, right? We would like to cut between A and B, okay, and this cut should be minimized because it's for this cut cost, okay. Let me try to put it here. Okay, this is the cut cost. Okay, for such cut cost, okay, it contains the weight of the edges connecting across A and B, Okay, and this can be actually this cut cost can be actually mapped to a certain area in the similarity matrix, right? So for instance, if now all the data points in the set A are placed on this portion, and the vertices in the set B are placed on this portion. Okay, so basically, if you try to reorder the data points according to if they are belonging to the set A and if they are belonging to the set B, right? Then the cut cost between A and B would be the summation of all the elements in this area of the similarity matrix, right? Because this area contains all the pairwise similarities between A and B, right? Between A and B. Okay. So basically, you would like to minimize the summation of the elements in this area of the similarity matrix, right? So that is the cut cost. That is related to the cut cost. Okay. But here comes an issue, right? So now try to imagine you have a data set. It's actually contains two groups of data. One is the red group, and then another one is the blue group, right? So most of the time when we see such data sets, for our human being, we will put a cut. Ideally we will put a cut here. Right? Such that the red dots and the blue dots, they are separated, right? And the cut cost is minimized. Okay, that is the ideal cut. Okay, but if you only use this objective function, okay, you only use this objective function of the cut cost and minimize it, then maybe you will have the result like this. Okay, to only cut out one single data point from all the others. Okay, so that means if you only try to minimize this objective function, very likely you will have a degenerate solution of having only one single data point in the first group and all the other data points in the second group, right? Okay, because you can see here, so maybe this kind of cards will give you smaller cut costs in comparison to the ideal cut, right? Because it's only need to consider the similarity from these data points to all the others, right? And also you might have another possible solution of the cut like this, but again, it's trying to separate a single data point from all the others. So these are the degenerate solutions, and it's not that good, right? It's not that good because it's not similar to what we actually expect for. Okay, so if you try to find other partition by only minimizing these cut costs, you might have such degenerate cases. Okay, so in order to avoid such a situation or such degenerate solutions, people would try to have some constraints on the in addition to the cut cost. We would try to have some constraints in addition to the cut cost. Okay, so later on we will introduce you two important algorithms. Okay, one is so-called the normalized cut, and another one is the ratio cut. And you can see here the normalized cut, right? In addition to the cut cost between A and B, we will have an additional constraint. And the same story for the ratio cut. In addition to the cut cost, we will have an additional constraint. Okay. Okay. So let's try to take a look about the additional constraint that different algorithms have. Okay. So in the normalized cut, this additional constraint try to minimize the summation of 1 over volume of the set A plus 1 over volume of the set B. And what is the volume? What is the volume here? The volume of the set A can be computed by this way. It's basically try to perform the summation of the degrees for all the data points in the set A. So basically, that is the summation of the degrees for all the data points in a specific group. Okay, so that means okay, I compute the inverse of the volume. I compute the summation over the inverse of the volume for each group. Okay. Okay, and in the ratio cut, the additional constraint is like this. Okay, it's a summation of the summation of 1 over the size of the set A plus 1 over the size of the set B. And the size here means how many data points you have in a specific group. So basically, it denotes the number of nodes in a specific group. Okay, in a specific group. Okay, so by using these additional constraints in order to avoid the degenerate solution. Okay, to avoid the degenerate solution. So basically, it might be easier to understand from these special cards, right? So basically, if you have this additional constraint, right, then ideally the solution you have, the solution of the partition that you are going to have, okay, it will have a property such that the number of the data points in these two groups, A and B, they are more balanced. So in other words, it's more likely that you are going to have the partition such that A and B, these two groups, they have roughly the same number of the data points, right? So if you have such property, then you can naturally avoid this degenerate solution, because you can see that in this degenerate solution, right, you might have one group containing only a single data point and another group containing all the other data points, right? So this, you can see the number of data points in this kind of degenerate solution, okay, is quite unbalanced for across different groups, right? Right, but by using the additional constraint, we are able to avoid such a degenerate solution. Okay, and now let's try to take these normalized cards as our main target to have the introduction. Okay, to continue introducing the basic idea behind the spatial clustering. Okay. Okay. So if you try to check this objective function used in the normalized cost algorithm, right? So again, this cost code, that is what we have learned, right? And for these terms, right? For these terms, okay, it is related to the volume. It is related to the volume of each groups, right? Of each groups, right? And again, if you try to check from the similarity matrix, okay? If you try to check from the similarity matrix, right? Then actually the volume of A can be represented by the summation of all the elements in this area, for all the elements in this area. Okay, so I think this is quite easy to understand, right? So basically, okay, let's assume in this portion is related to the data point of group A, or we say of set A, right? And so first, if you want to compute the volume, you need to first obtain the degree of all the data points in the set A, right? So the degree, how to compute the degree? As I said, the degree can be computed by the summation over the specific row, right? The summation of the row related to a specific data point I. Okay? And now if we know all the data points in this portion, they are from the group A, then basically we try to sum up all those rows. Okay? So basically this volume A can be easily mapped to a specific area in the similarity matrix, right? Okay? So you can see here, right? In these normalized costs, you have the cut cost AB, and you have this term. This term is related to volume A and the volume B. And no matter for the cut cost AB or the volume A and the volume B, they can be all mapped into specific regions of the similarity matrix. Okay, and I'm going to show you that. Okay, so again, in this similarity matrix, okay, this area is related to the volume A, and this area is related to the cutoffs that you want to minimize for, right? And if you try to observe layer connections, right, you can see that the volume A, this area, if I try to, I try to discard this area. If you try to discard this area, or try to subtract this area, okay, then you can come up with the cut cost AB. You can arrive the cut cost AB. Okay, and this area is actually the diagonal region. This is just like a diagonal block. It's just like diagonal block, right? And for this block we name it association of the A. Okay, because all this block is related to the set A. Okay, this is so-called the association of the set A. Okay, of the set A. And actually, we can use another way to represent these parts, Okay, so intuitively, right? This part is trying to describe the pairwise distance between all the data points in the set A, right? Okay, this part only contains the pairwise distance between all the data points in the set A, right? So basically, we can define a indicator vector. We can define a binary indicator vector, right? So this indicator vector its size is n by 1. Okay, it's n by 1. And if we put all the elements related to the set A equal to 1, and all the other elements equal to 0, right? Okay, so that is the indicator vector. So in another way of thinking, right, this is a n by 1 vector, right? Then for all the data points belonging to the set A, I give the corresponding element equal to 1 and all the others equal to 0. So that is trying to indicate which vector is in, this vector is trying to indicate which data point is belonging to the set A, right? Okay. So if you have such indicator vector of the set A, and this is somehow binary, okay, and then you can try to perform this computation, right? F transpose times the similarity matrix times F, then you are able to obtain the association of A, right? You are able to obtain the association of A, the summation of all the elements in this region, right? Okay. And now if we try to put it back again, if we try to put it back again in this kind of illustration, right? So now the association A can be computed by F transpose times W times F, right? And actually the volume A can be computed by the F transpose times the degree matrix times F. Okay, this you can easily check on your own. Okay. Okay, so now the volume A can be represented by the F transpose times the degree matrix times F, and the association of A can be computed by F transpose times similarity matrix times F. Then the cut cost AB, okay, can be actually computed by the F transpose times D minus W times F, right? Because Here you can see this is just a subtraction, right? So you simply try to perform a subtraction between these two terms, between the volume and the association of A, and you obtain the formula describing the calculus AB. Okay, so basically here, D minus W, the degree matrix minus the similarity matrix, this term has another name. It is so-called graph Laplacian. This is so-called graph Laplacian. Okay, so we define a special matrix L. Okay, we define a special matrix L. Okay, is computed by the degree matrix minus the similarity matrix. Okay, and actually for this graph Laplacian matrix, it has some quite important properties. Okay, so here I try to put the properties. I try to provide you the important properties of this graph Laplacian matrix. Okay, and actually for these properties and all the I think most of the important materials related to the spatial clustering you can find out from this tutorial. This is a very nice, very good tutorial that I suggest you guys can all spend some time to read it. Okay, you can definitely have a deeper understanding about the spatial clustering. Okay, and these slides is actually cropped from this tutorial. So you can see this is actually this tutorial is well organized and provide you a very detailed description about the spatial clustering. Okay, so let's try to check the properties of this graph Laplacian matrix L. So basically, the matrix L satisfies the following properties, right? So for every vector f, okay, for every vector f we have, okay, for every vector f, okay, if you try to compute the f transpose times L times f, then actually it can be expanded by this way. It can be expanded into this way. Okay, so Wij here is the elements from the similarity matrix, and the Fi minus Fj. So the Fi here means the ith element of this F vector, and Fj here again it means the jth element from this vector F. Okay. So basically, the F transpose times L times F can be represented in this formula. So can be represented by this formula. Okay, you can simply check on your own by following these equations. Okay, it's actually quite straightforward. Okay, and the L is symmetric and positive semi-definite, right? It's basically symmetric because it's quite easy to understand, right? Because the L is defined based on the degree matrix minus the similarity matrix, right? And both the degree matrix and similarity matrix are symmetric, right? So D minus W, of course, is still symmetric, right? And this is positive semi-definite, right? Because the F transpose times L times F can be represented by this term, right? Right? Okay. And you can see here this term, right? You always have the you always have this Fi minus Fj square. So this is always positive, a positive value. Wij is always bigger or equal to 0, right? Because this is a similarity, right? So it's always bigger or equal to 0, right? So this is always bigger or equal to 0, and this is always positive. Their product will be always bigger or equal to 0, and the summation over these terms will be always bigger or equal to 0, right? Okay, and the positive semi-definiteness is a direct consequence of the first property. which shows that the F transpose times F, the F transpose times L times F will be bigger or equal to 0 for any arbitrary, actually for any arbitrary vector F. Okay, for any arbitrary vector F. Okay, so that is the positive semi-definite, right? So this is what you actually need to know from the linear algebra course, right? And the smallest eigenvalue of L is equal to 0, is 0, and the corresponding eigenvector is the constant 1 vector, is the constant 1 vector. Okay, so this could be also easy understood, right? This can be easy understood, right? So if you try to if you try to write down the eigen if you try to write down the eigen decomposition problem of the L, right? You might have the eigen decomposition problem. Okay, is actually let me try to use this. Okay, so you have the matrix L, right? Let's say is eigenvalue is, let's say is F, right? Okay, then its eigenvalue is lambda times F, right? So lambda F. Okay. So this is the eigen decomposition problem of your Laplacian matrix L, right? Okay. And actually the smallest eigenvalue of this matrix L is equal to 0, right? Okay, it's equal to 0, so that means the lambda equal to 0, and the corresponding eigenvector is the constant 1 vector. Is a constant 1 vector. Okay, it's a constant 1 vector. Okay, so if you try to consider from here, right? If I put the eigenvector, which is the constant 1 vector. So what is the constant 1 vector? That means this is a vector with all its elements equal to 1. With all its elements equal to 1. Okay, with all its elements equal to 1. Okay, so if you have L multiplied with the constant 1 vector, okay, with the, okay, if you have L is multiplication with the constant 1 vector, right? Okay, so actually, I hope you guys can see this easy. Okay, so because L is equal to Z minus W, okay, and now if you have the okay, let's try to see this. Okay, if you have such much, sorry, should be like this. Okay, so if you have your L multiplied with the constant 1 vector, right, it will be equal to have the D minus W times the constant 1 vector, right? And it can be represented by it can be further expanded by Z, your degree matrix, times the constant 1 vector, minus the similarity matrix times the constant 1 vector. And you can see actually because D is a diagonal matrix, right? Its multiplication with the constant 1 vector will become a vector, will resolving a vector with all its elements, the degrees of the data points, right? And if you have the similarity matrix multiplied with the constant 1 vector, right? Then you will always end up with a vector. You will also end up with a vector that all its elements are the degrees, right? So of course, this will end up equal to 0. Okay, to 0. okay, to 0. Okay, so the L multiply with constant one vector will equal to 0, and now the eigenvalue lambda is also equal to 0, and times this one vector, it will be also a 0. It will be also a 0 vector, right? Okay, so from here you can see actually okay, so maybe I can put it like this. Okay, just keep it in this way. Okay, good. So you can see here, right? From such observation, right? We can see that the smallest eigenvalue of L is equal to 0, and the corresponding eigenvector is a constant one vector, right? And why we can tell that the 0 is the smallest eigenvalue is because the L itself the L itself is positive semi-definite. It's positive semi-definite. So 0 is already the smallest the smallest possible eigenvalue of L. Okay. Okay. Okay, and the fourth property of this matrix L, this Laplacian, this graph Laplacian matrix, is that L has n non-negative and real-valued eigenvalues. Okay, okay, this is a direct consequence of the previous three properties, right? Oh, we already know the smallest eigenvalue is 0, right? And L itself is an n by n matrix, so it will have n non-negative. It will have n eigenvalues, right? But now the smallest one is 0, so all the others will be non-negative. Okay, will be non-negative. Okay, so those eigenvalues can be represented in this by this variable, right? The smallest one is 0, and then you have so that means the lambda 1. The lambda 1 is equal to 0, and all the others, lambda 2 to lambda n, they are bigger or equal to the previous eigenvalues. Okay, so that is the property of the graph Laplacian matrix. Okay, so you can see here we are now already able to link these graph Laplacian matrix to some nice properties from the eigen decomposition. Okay, from the eigen decomposition. Okay. 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 And now we would like to have more understanding about the graph Laplacian matrix. Okay. So the first one is that actually we are able to tell from the graph Laplacian matrix about the number of connected components, right? Okay. So so what is the connected component? What is the connected component? Maybe I can try to show you some examples. Let's try to see if I do have the figures around here. Okay, maybe I don't have. I can quickly draw you one so you can have a brief understanding about the connected component. Okay, so we simply assume that we have some data points. Okay, have some data points in our data set. Maybe okay. Okay. So you might have some data point like this. You might have some data point like this, and some data points like this. Okay, and then we define a similarity measurement. Okay, then if according to this similarity measurement, okay, then you would end up with this kind of situation. Maybe I should I should reduce the number of the nodes. Otherwise, I would take too long to draw it. Okay. Let's see. Sorry, take a little bit. We'll take a few seconds to do it. One more, two more. Sorry. Okay. So if you now have a data set, then and according to the corresponding definition of the similarity, we end up with this kind of graph. Okay. So you can see here, this is one independent graph, and another one, and here comes another independent graph, right? Although they are from the same data set, but now it contains the independent graph like this. Okay, then for each independent graph, we name it the connected component. We name it a connected component, right? Okay, so actually, what we are going to tell you is that according to this graph Laplacian matrix, we are able to understand how many connected components in your data set. How many connected components in your data set? Okay. Instead of directly draw out. Okay. Instead of directly drawing out the graph representation in this way, we can simply use the computation. We can simply from the computation, right? We can simply use the computation L equal to D minus W, and then perform some analysis on the matrix L. Then we are able to understand how many connected components you are going to have in this similarity graph. Okay. So let's first assume there are multiple connected components. The K here represents how many connected components, and let's now assume we have multiple connected components given a similarity graph, given a similarity matrix. Okay. So actually, for each connected component, it has an associate Laplacian. Okay. And therefore, we can write the matrix L for the overall graph as a block diagonal matrix, block diagonal matrix, right? Because for each across the connected components, there is no connection, right? So the graph Laplacian matrix for the overall data set can be written as a block diagonal matrix, and in this block diagonal matrix, for each diagonal block, okay, is contained the graph Laplacian matrix from each connected component. For example, L1 here means the connected component. The L1 here means the graph Laplacian matrix from the first connected component. LK here means the graph Laplacian matrix of the kth connected component. Okay, and each block here, right? Because each block here corresponds to a connected component, and therefore each matrix Li has an eigenvalue 0 with multiplicity 1, right? So for example, for this L1, this small, sorry, I should not say small. For the L1, this graph Laplacian matrix for the first connected component, right? We know this L1 matrix, it has one eigenvalue, the smallest eigenvalue equal to 0. Okay, and Okay, and all the others, all the other blocks, for each of the block, you will contribute to one eigenvalue equal to 0, right? Okay, so overall, because in these L matrix you have k blocks, every block will have an eigenvalue 0. Okay, so the 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 L matrix, the L matrix is now having uh, k eigenvalues equal to zero, right? Because the I hope you can see this from your understanding of the linear algebra, right? Because L now is a block diagonal matrix, then for every block, it has a eigenvalue equal to 0, right? Then the spectrum, right? The spectrum basically the spectrum here is related to the eigen decomposition, right? The spectrum of L is given by the union of the spectra of Li of so many blocks. Okay, so because the spectrum of L is given by the union, right? So now you have k blocks. Every block will contribute to one eigenvalue equal to 0, right? So their unions will have the property that that it has eigenvalue equal to 0, and it has eigenvalue equal to 0 and with multiplicity k. So that means that in another word, that means this matrix L has k eigenvalues equal to 0. Okay. Okay. So according to this property, right? Given a similarity graph, we can first compute its corresponding Laplacian its corresponding graph Laplacian matrix L, and then we try to perform the eigen decomposition of this matrix L, and then we try to check how many eigenvalues are equal to 0. Then, according to the number of eigenvalues equal to 0, then we are able to tell how many kinetic components are in this similarity graph. Okay, that is the basic idea we want to show you here. Okay. Okay. So okay. So again, we would like to have a deeper look, right? Let's assume there are multiple kinetic components, right? So that means this graph Laplacian matrix has k eigenvalues equal to 0, right? And the corresponding the so for each eigenvalue equal to 0, right? Okay, they are from their corresponding eigenvectors. Let's try to check their corresponding eigenvectors, right? Okay, so for the let's say maybe so for the first block L1 from maybe I should okay for the first block L1 is from the first kinetic component, right? Okay, then for this kinetic component, right? For this kinetic component is corresponding one vector, right? So I hope you still try to remember it. Wait a minute. What? Wait a minute. Let's skip this one. Okay. Okay, maybe I can come back to this slide later because it seems like I ignore this slide as the first time. Okay, sorry. Okay, but anyway, for this L1 block, right? The eigenvector corresponding to its eigenvalue, okay, basically will be the one vector related to all the elements in the first connected component, right? Okay, so for example, we say in our data set x1 to xn, okay, maybe x2, x4, and x5 are from the first connected component, right? Okay, so now for the L1 is one vector should be having one for x2, x4, and x5, and 0 otherwise, right? Okay, so basically, right? Let's assume the overall data set the overall data set has let's assume our data has 13 data points, and for a specific for the case connected components, right? The x5, x6, x7, x8, and x9, they are from the case connected component, right? So the one vector corresponds to the zero eigenvalue of Lk, okay, is actually can be represented by this way. Okay, this one vector with one on the elements corresponding to the case corresponding to a case connected component and 0 otherwise, right? So that means for every connected component, right? For every connected component, we have the L1 to Lk, right? Then for every L1 to Lk, they have their own eigenvalue equal to 0 and the corresponding eigenvectors in the form like this. Okay, and these one vectors are actually the indicator vectors of the graph connected component, right? Because they are indicating which data points are belonging to which connected component, right? Okay, so these one vectors for each connected component are actually the indicator vectors. Okay, Okay, and of course, when we sum up all the indicator vectors, or we say when we try to sum up all the one vectors for all the connected components, right? You will become a one vector which size is it will become a one vector which size is n by 1 and all the elements equals 1, right? Okay, I hope this can be easily understood. Okay, and let's go back to these slides, right? Okay, previously we described the cases that you have multiple connected components, right? And we say the eigen decomposition when you perform the eigen decomposition of the L, right? And you simply need to check how many eigenvalues equal to 0, then you are able to understand how many connected components are now in your similarity graph. Okay, and if we now assume there is only one connected component, that means now your graph is fully connected. Right? So this is similar to a case that your similarity graph only has It only has one connected component, and all the elements, they are connected to each other. Okay, this is the so-called fully connected graph. The fully connected graph. Okay, the fully connected graph. Okay, if you now only have one single connected component, that means your graph is fully connected, right? And if you try to consider its eigen problem, if you try to consider its eigen problem, right? Okay, then according to what we have mentioned here, right, it has the smallest eigenvalue equal to 0, and the corresponding eigenvector of this 0 eigenvalue is a 1 vector. It's a 1 vector. Okay, it's a 1 vector. And okay, so and according to the first observation, right, the F transpose times L times F for any arbitrary F, it can be written in this analytical form. Okay, it can be written in this analytical form, right? Okay, and let's now assume we have a U vector, and we perform U transpose times L times U, and you will actually end up with this term. Okay, and if we and now if this U is a eigenvector, it's an eigenvector of L. It's an eigenvector of L. And then if the U is if the U now is the eigenvector related to the smallest eigenvalue, then it will be, this term will be equal to 0. This term will be equal to 0, right? This term will be equal to 0, right? Okay. So now Wij, as we say, is always bigger or equal to 0, right? Okay, and Ui, and you have this Ui minus Uj square, right? Okay, so that means this term is always bigger than 0, and this Wij is either equal or is always bigger, or is either bigger or equal to 0, right? Okay, so if any two vertices are connected by a path, that means the Wij equal to 0, then the U needs to be constant at all vertices, such that the quadratic form here, Ui minus Uj square, vanishes, right? Vanishes, right? Because if now all the Wij, if all the Wij are bigger than 0, then this quadratic form should be equal to 0. Otherwise, you cannot sum up. You cannot sum up to 0, right? So that means Ui and Uj should be, for all the Ui and Uj should be equal to 0. All the Ui minus Uj should be equal to 0, and that means all the elements in U, all the elements in this U vector, they are equal to each other. They are equal to each other, right? So therefore, a graph with one connected component has the constant vector as the only eigenvector with eigenvalue 0. Okay. So this description is trying to give you an idea. It's trying to give you an idea. Okay. It's trying to give you an idea. Okay. When we know that L is a when we know that the L is its smallest eigenvalue is equal to 0, then given these eigenvalue equal to 0, then we try to check its corresponding eigenvectors, right? We try to check what is the corresponding eigenvectors, right? And when we try to check the corresponding eigenvectors, and according to these descriptions here, we know that, oh, this L matrix, okay, its smallest eigenvalue, or we say its zero eigenvalue, will only have a eigenvector, will only have a single eigenvector, and this eigenvector is a one vector. It's a one vector. Okay. 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 So that is the basic idea. That is the basic idea. Okay. Okay. And so far we have described you that okay, according to the eigen decomposition, of your graph Laplacian matrix, then you are able to tell how many connected components are in your similarity graph. Okay. Okay. So now let's give you an example. Okay. So so let's assume you have a data set. Okay. This data set. This data set is basically a 1D data set. So you have a lot of 1D data points. Right? And in this 1D data set, okay, you basically contain the values from four Gaussians. Let's say from four Gaussians. The first Gaussian, its mean is around value 2. The second Gaussian its mean is around value 4. The third Gaussian its mean value is around value 6, and the third Gaussian, the fourth Gaussian, its value is around value. Sorry. Okay, so for the fourth Gaussian, its mean value is around 8. Okay, and those Gaussians, their variance is pretty small. Let's say. Okay, so if you have such data set, okay, you can imagine that you have a bunch of data points. Their value are around 2, and another group of data points, their value are around 4, and so on. Okay, so here is just trying to show you the histogram of the samples, right? So on the x-axis are their value, and on the y-axis will be the how many data points are with certain values. Okay, but anyway, given such 1D data set, now let's assume our graph is built by using the k-nearest neighbor, right? So that means for a single data point, it is only connected to its first k neighbors. Okay. Okay. So you can imagine that this graph is not fully connected, right? So I hope you can imagine, right? Because now we have in our whole data set, we roughly have 4 groups. The first group has value around 2. The second group has a value around 4, and the third group has value around 6, and the fourth group has value around 8. And for each group, all the data points within this group, okay, all the data points within this group will be connected, right? They are not okay, because they are built by using the k-nearest neighbor, okay, to find out the connection between the data points, right? So you will not have the edge between 2 data points, which is with value 2 and which is okay. Maybe I should say it again. You will not have the situation that you connecting 2 data points. They are with, for example, value 4 and value 8, right? Because there's no chance for them to be the k-nearest neighbor of each other, right? Okay. So now if we have such data set, and we use the k-nearest neighbor to build up our similarity graph, then you can already imagine there will be four connected components. There will be four connected components, right? If we have such simple data set, then you can already imagine that we have four connected components in our graph. Okay, so ideally, if you have okay, theoretically, if you have four connected components in your similarity graph, right? Then the graph Laplacian matrix should have four eigenvalues equal to zero. Should have four eigenvalues equal to zero, right? So you can try to okay. So actually that can be easily verified if you build up this data set on your own, and then you, based on this data set, you build up the similarity graph, okay? And by using this similarity graph, you try to compute the corresponding graph Laplacian matrix, and then you try to do the eigen decomposition, and then you will find out actually, yeah, there will be four eigenvalues equal to zero, and all the other eigenvalues, they are bigger than zero. They are bigger than zero. Okay, so you can set up your own toy data set and perform such computation to verify what we have learned about the connection between the number of zero eigenvalues to the number of connected components. Okay, and okay, so now according to the eigen decomposition of your graph Laplacian matrix, we have four eigenvalues equal to zero, and if you try to check the corresponding eigenvectors of these four eigenvalues, okay, and then you can try to visualize them. Okay, you can try to visualize them. Okay, you can try to visualize them, and then you might be able to see this kind of format of the eigenvector, right? Okay, so here we try to visualize the first eigenvector related to the zero eigenvalue. Okay, and this figure shows that for all the data points around value 4, for all the data points, if their value are around 2, then their corresponding element in the first eigenvector is 0. But if you are but for those data points whose values are around 4, then their corresponding element in the eigenvector will be with a positive value. Okay, and again, for other data points whose values are around 6 or 8, again, their corresponding element in the first eigenvector will be equal to 0, right? So you can see that from such eigenvector, is actually related to the indicator vector of the partition, right? So for example, here the first eigenvector can be treated as an indicator vector for the group related to value 4. The second eigenvector here can be treated as an indicator vector for the group corresponding to this value 8. The third eigenvector can be related to the indicator vector for the group of value 2. Okay, and for the fourth eigenvector, it will be related to the indicator vector of the group with value 6. Okay, and you might have a confusion here. Why the second eigenvector looks like in this way? It looks like in this way, but actually it's quite easy to understand, right? So it can be easily think of that because all the elements around value 8, they are with the same value 0, and all the others are with another constant value, right? So it's actually, maybe it's not a typical form. It's not a typical form of the indicator vector, but it still provides us something like the indicator vector, right? Because it indicates that all the elements around value 8, they are in the same group, and all the others are belonging to another group, right? So that is the that is similar to the idea of the indicator vector. Okay. So basically, okay. Here, according to these example, okay, we not only try to verify the idea that we just mentioned, okay, about the number of the number of zero eigenvalues and the number of kinetic components that should be equal to each other. Okay, we not only want to express this idea to you, but another important idea I want you guys to remember is that the eigenvectors of your graph Laplacian matrix L, okay, the eigenvectors of your graph Laplacian matrix L, okay, are actually closely related to the indicator vectors of your partition. Okay, that is the maybe that is one of the most important message that you need to remember about the graph, about the spatial clustering, about this graph partition, because the eigenvectors of your graph Laplacian matrices, they are closely related to the indicator vectors for your partition. Okay, so I want you guys to really remember this idea. Okay, Okay, then you might also ask about how about the fifth eigenvector, okay, and all the other eigenvectors in the following. Actually, they can be another, maybe they can be also some forms. They are also closely related to the indicator vector. Why? Because if you try to check these eigenvector 5, you can see here roughly all the data points with value 8 or 6, okay, and okay, all the data points of 8 or 6, or I think around 4, right? They are belonging to they are corresponding element in the fifth eigenvalue, in the fifth eigenvector. They are with the same value, right? And the data points in the second okay, so for those data points with whose value are around 2, their corresponding elements in these fixed eigenvectors, they are with another with some other values. Okay, so this can also be this can also be related to the indicator vector on the partition, because it's trying to separate 4, 6, 8 from 2, right? Okay, okay, and later when you try to visualize all the other eigenvectors, we can also try to define a threshold, maybe. Okay, you can first try to define a threshold, and then that threshold. So for example, I put a threshold on the values. I put a threshold on the values for the elements in my eigenvector. Then it will provide you a certain partition between the data points. Okay, so even this is not a very nice form of the indicator vector, but after we perform, for example, the thresholding on the values of the elements in the eigenvector, then it is still able to provide us the hint or the idea about the possible partition. Okay, okay. But anyway, again, I want you guys to remember that the eigenvectors of the graph Laplacian matrix L, they are closely related to the indicator vectors on the partition. Okay. Okay. So before we go into another example, okay, I just want to show you more understanding on the graph Laplacian matrix. Okay, so the first non-null eigenvalue, okay, the first non-zero eigenvalue is called Fiedler value. It's just a terminology, okay, and the corresponding eigenvector for this Fiedler value is called a Fiedler vector. Okay, okay. And again, for a fully connected graph, okay, its smallest eigenvalue is equal to 0, and the corresponding the eigenvector corresponding to the smallest eigenvalue is a 1 vector. It's a 1 vector. Okay, it's a 1 vector. Okay, and then okay, then the U2, right? So here we say that U1 is the eigenvector related to the zero eigenvalue, right? And for a fully connected graph, we only have one eigenvalue equal to 0. Then for the second eigenvalue, it will be actually the Fiedler value, right? So the corresponding eigenvector U2 is actually the Fiedler vector. Okay. So the eigenvectors form an orthonormal basis, right? So that is the basic property of the eigendecomposition, right? So when you perform the eigendecomposition of a matrix, then those eigenvectors, they will be also normal. They will be also normal, right? So that is what you should have learned from your linear algebra courses. Okay. So now we know that. Okay, we know that. Okay, the first eigenvector related to the the eigenvector related to the 0 eigenvalue, U1 is a 1 vector, right? It's a 1 vector, right? Then all the other eigenvectors, for example, U2 to UK, okay, from U2 to from U2 to UN, okay, all the other eigenvectors, okay, they are also normal to the first eigenvector, right? Okay, again, from the linear algebra, right? All the eigenvectors, they are also normal to each other. Now we know that the first eigenvector of the graph Laplacian matrix is a 1 vector. It's a 1 vector, right? It's a 1 vector. And all the other eigenvectors should be also normal to the first eigenvector, and the first eigenvector is a one vector. It's a one vector. So that is to say, for any arbitrary, maybe I should say, for all the other eigenvectors, okay, because of the orthogonality with respect to the first eigenvector, so their inner product will equal to zero. Their inner product will equal to zero, right? Their inner product will be equal to zero. Okay, so that means it for every eigenvectors, instead of the first one, for every eigenvector, if you try to sum up its values, okay, for every eigenvector, if you try to perform the summation over its values over its elements, then it will end up with zero. Okay, it will end up with zero. Okay, this will end up with zero. That is what we try to write down here. Okay, that is quite an important property actually. Okay, and that is related to the Greif-Laplacian matrix. Okay, so I think we can stop here, and then we will continue on another example next time. Okay, we will continue on this example next time. Okay, and I really encourage you guys to read this tutorial and to get more detailed understanding about the special clustering. Okay. Okay. Thank you.